Good morning, and today we are going to continue from the previous lesson. In the last lesson, we are dealing with SCR and the equivalent circuits operation, which normally referred to as the transistor analogy. Today, we are going to start to continue on something on turning on or triggering the SCR. The meaning of triggering is to put the SCR into conduction state, and this time we are going to deal with whatever I'm referring to as the methods used in triggering the SCR. So basically, there are several methods used. There are several methods used to trigger SCR, and we're going to start with whatever I'm referring to as the forward breakover voltage, forward breakover voltage. In this case, the voltage applied across the SCR must exceed the must exceed the barrier voltage across the junctions. In this case, the voltage applied across the SCR must exceed the forward breakover voltage and turn on the SCR. There's another thing I want us to discuss concerning this method is that once the forward breakover voltage is exceeded, the conduction is mainly on the avalanche region. So we're going to discuss the method number 2 for starting this is the gate triggering. Whatever happens in this case is that the applied voltage must be slightly greater than the rated forward breakover voltage. The applied voltage is slightly greater than the forward. The applied voltage is slightly greater than the forward breakover voltage. And as a result of this, the SCR is turned into conduction using the gate pulse. And as a result, the SCR is turned into conduction using the gate pulse. Then we are going to have the method trigger number 3 is what I refer to as rate effect or rate of change. Rate effect, or whatever referred to as dV dt triggering. So from this one, we are dealing about the rate of change of voltage across the terminals of the SCR, and therefore in this case it's due to the rate of change or the rate of change of the anode to cathode voltage. So the SCR is triggered into conduction by a rapidly changing voltage across its terminals. And lastly, we are going to have what I refer to as light triggering. So with light triggering, we are going to direct a certain beam of light across the junction so that the junction J2 is put into conduction before the actual flow. So in this case, a beam of light is directed to junction J2, whereby the conduction is enhanced so that electrons from J1 can easily flow across the SCR terminals. So once we know how to turn on the SCR, we now go to understand how can we turn it off, because that we are able to use it as a control point. So we're going to talk about turning off SCR. So there are basically two methods of turning off an SCR, and one of which is that we are going to apply a voltage that actually is below the conduction voltage. And another thing, we are able to do that, we can also turn it off by actually reducing the current to below what we refer to as holding current. So for us to do this, so let us understand that once the SCR is turned on, it remains conducting until the point whereby the applied voltage across its terminal is reversed. So number one is the SCR can be turned on, can turn off by applying a reverse bias voltage across its terminals. By so doing, junctions J1 and J3 will be enlarged, hence blocking the flow of Number 2, by reducing whatever referred to as holding current, by reducing whatever referred to as by reducing the holding current. By reducing the holding current to below the minimum value. Take note that holding current is the minimum current that we require for the SCR to remain conducting. So once we are able to understand that this current, once reduced below the holding current, automatically the SCR will not conduct, because for it to remain conducting, we must have the holding current. So from this, we're now going to understand or to sketch something on the VI characteristics of the SCR. So VI characteristics of SCR. So we need to sketch this so that we're able to understand what it's all about and how the conduction is processed. We shall have the vertical and the horizontal axis. So this is the characteristic of the SCR. And when you look at this, you need to understand some of the things of what happens at different points. So we can see that the origin is at point O. And we have got the upper part of it in the first quadrant being A, B, C. And in the third quadrant, we have got D and E. So when explaining the operation of this, we need to understand what happens between point O and point C and point B. And another thing is point A, point B, and point O and D, and point D and E. So we're going to understand one of the things that happens in this situation, that for us to understand this is that at this point here, the SCR, here we're talking of, this is a forward breakover voltage. Forward breakover voltage. And this will talk as reverse breakdown voltage. So we also are going to have this whatever referred to as IT and IH. IH is the holding current and IT is the turn-on current. So I want to explain this in around 4 statements. 1, between point O to point C, the SCR was off. But when we move slightly above the forward breakover voltage, the SCR turns on. So at this point, the forward breakover voltage, when you reach the forward breakover voltage, when the voltage is increased above that voltage, the SCR turns on. Once the SCR turns on, then we are going to look at to see that the resistance across the junctions reduces, and therefore the current now falls. So once it turns on, the current falls, and you maintain the minimum current, which we refer to as the holding current. That holding current is slightly below the turn-on current. IT is the turn-on current, and holding current is the minimum current required for the SCR to remain conducting. So between point B and C, the resistance reduces, and the current reduces because conduction as the SCR turned on. The resistance reduces and the conduction now is improved. So point B and C, the SCR acts as a normal diode. because it conducts in the linear region of the diode the way it conducts. And then therefore, the applied voltage is directly proportional to the current flowing across the SCR. That is in the forward conduction. And the reverse conduction, where it's in the fourth quadrant, we have point 0 to D. Point 0 to D, the reverse voltage is still less, so the SCR is still off. But when the reverse voltage is increased beyond the reverse breakdown voltage, the SCR is forced into conduction. When it's forced into conduction, then we shall have a surge of current flowing between the anodes of the SCR, the anode to cathode of the SCR. And that's why there's a sharp drop here in current flow. So that's what it is. So we're going to give this in terms of details and terms of the different points and how it can be explained well. So we can start at point OC. Point OC. The applied voltage is increased. Is increased to a voltage above forward breakover voltage, where the SCR is turned on. Before, the forward breakover voltage is reached, little current flows in the forward direction, mainly due to the junctions being forward biased. At point BC, there is a drop. There is a drop in current from the turn-on current to holding current, IH. Turn-on current is IT, to holding current, IH. So once the SCR is triggered, the conduction goes to minimum, holding current. Then point AB, the SCR response. The SCR responds like a normal, diode, and the applied voltage is directly proportional is directly, the applied voltage is directly proportional to the current flow, i.e., it obeys Ohm's law. At point OD, at the fourth quadrant, then the applied reverse voltage is still below the reverse breakdown voltage. And so, little current flows in the reverse direction, what I refer to as the leakage current. And lastly, point DE. When the voltage applied in the reverse direction exceeds reverse breakdown voltage, exceeds reverse breakdown voltage, the SCR junctions, the SCR junctions are destroyed, and there is an increase in current flow across the SCR. So we can now look at where we can apply this SCR as a device so that we are able to utilize the component in different areas. So we can talk of applications of SCR. Applications of SCR. So we can have number one as motor speed control. Speed control. We can talk number two as battery chargers. And number three, we can talk of relay control. And number four, we also have what we refer to as phase control in power supply systems. Phase control. Number five, we can talk of the heater control. And lastly, number six, there are so many, but let us just study some of the things we need to utilize. Light dimming in disco lights, light dimming control in entertainment. So we're going to study Our last component, we're going to study our last component. So always we have to start with the construction and the symbol and maybe the equivalent circuits. This time I'm going to draw them at once because at least we are familiar with the kind of expectation that we need to have. So this is the track and this is the construction. We're going to realize that the track has got two terminals, MT1 and MT2 across the ends, but it has also got another gate, which is the third terminal. But another thing we're going to realize that the construction is such that we have got two NPN, we have got two junctions, J1 and J2. Maybe I can put J1 and J2 here, so that can be able to see two junctions, but we still have the NPN and PNP transistor connected back to back, and also NPN, and also the third terminal which is from the gate. When you look at all the symbol looks like this, it appears to be an SCR that's connected back to back with MT1 and MT2 terminals remaining the same. The equivalent circuit also appears the same, but in this case we are going to realize the gate of the two SCR that are connected back to back is projected on the outer end so that it can be easily explained. Once we have this, then it's very easy for us to understand that how this thing operates. So we are going to describe the operation. The construction is very simple because it's made of two NPNs, of two NPN and PNP transistor connected back to back, and this is how it appears like. So we are going to talk about the construction, the operation, not the construction, the operation, so that we familiarize ourselves with the best way possible, so that we know how the device is being used. So anytime we're explaining the operation, we must understand the operation must allow us to have the movement between MT1 and MT2. Then it becomes very easy. And this track operates only in 4 modes, but 2 modes are preferred. And these 2 modes that are preferred are the ones that is being used when using the track as a device. So that it becomes very easy for us to use that. So the track operates on 4 modes. The track operates on 4 modes. So we have mode number 1. When the MT2 is positive, when the MT2 is positive and G is positive, and G is positive. So we should have the figure, the picture, whatever we're talking about that. When MT2 is positive and G is also positive, then what should we expect? So in this case, the operation of the track is identical to SCR. And given that we are talking about the SCR, it's very easy. Full stop. The current through the current through the switch is given as P1, N1, P2, N2, P1, N2, and from MT2 to MT1, and from MT2 to MT1. So we have done with the first operation, the first mode of the four modes. We are going to go to the second mode. The second mode is when the MT2 is negative and G is positive. When MT2 is negative and G is positive. Take note that G is the gate. The current flows through the switch. Flows through the switch. It flows through the switch P2N1, P2N1, then P1, N4. And the currents from MT1 to MT2. And the flow is from MT. The flow is from MT1 to MT2. So when you look at this diagram also, look at the construction diagram, you can be able to figure out this very easily. When we talk about the mode number 3, when MT2 is positive, and gate is negative, when MT2 is positive and gate G is negative. Current flows through the switch P1N1, P2N2. Flows through the switch P1N1, P2N2, from MT2 to MT1, from MT2 to MT1, from MT2 to MT1. And this mode gives us a poor conductivity, so it's not very much preferred. This mode has poor conductivity, and so not very much preferred. So we're going to the fourth mode, when MT2 is negative and G is negative. When MT2 is negative and G is negative. What is our expectation? The current flow from P2N1. Current flows through P2N1, P1N4, P1N4. And this mode is slightly efficient. This mode is slightly efficient than mode 1. than mod 1. So these are the four modes that the Triac operates in. So when you're asked to determine or to identify the modes that are preferred, then we only have mode 1 and mode 4 being the preferred modes of operation. And therefore, the mode 2 and mode 3 are not preferred. And remember, for us to use the Triac for conductivity, we must look at the maximum conduction that is required. So we are going to have a sketch of the VI characteristics of the Triac so that we also compare it with these other devices. So these are the labeling of the axis. So when you look at this OABC is identical to ODEF. And this is how it appears now. The vertical axis for current and the horizontal axis is for voltage. So when we are asked to explain, then we just need to explain this, and when the reverse happens, then this curve is going to be applied. So the curves OABC and ODE are identical in nature. And even from the shapes, then have identical in nature. So how do we then determine the best way possible? So chances are that because of the preferred mode, this is mode 1 and this is mode 4. That the ones have made a choice about the modes of operation. Because I was just told you from the previous statement that the mode 1 and the mode 4 are the most preferred mode of operation, and they must be reflected. So quadrant 2 and quadrant 4 here is not applicable for that. So we're going to explain that in details. So the first statement, we need to understand the curves OABC. The curves OABC and ODEF. ODEF are identical to the forward characteristics, to the forward characteristic of the SCR. So whatever we have as expression, the SCR can also apply this. So another thing to understand is point OA, the SCR is off. Point OA. Point OA, the Triac is off, not the SCR. The Triac is off until the applied voltage of either polarity exceeds applied voltage of either polarity exceeds the forward breakover voltage. So the third point we shall have there is that the Triac will only conduct. The Triac will be turned on and remain in the conduction mode. Remain in conduction mode as long as the conduction current does not fall below the holding current. So in this case, the conduction current is the triggering current, and the holding current is the minimum current for the triac to remain conducting. And lastly, we have to know that as the value of the gate current is increased above 0, so number 4, as the value of the gate current is increased above 0, then what should you expect? The SCR background voltage is lowered. The SCR, the Triac forward breakover voltage is lowered, and this makes it suitable for easy turning on of the device. We are also talking about the applications of the Triac. So we need to have some application of the Triac. They're nearly similar to the SCR in almost all aspects because they're just identical. So we have the phase control, number 1. We can talk, number 2, of the motor speed control. Number 3, we can talk of the heater control. We can talk, number 4, is of the static switching. What I refer to as static switching. Static switching in AC power. And lastly, for among the examples I'll give you is the light dimming control. So I believe we can now have our last device, which is our Triac. The last component we shall have in discussion on this topic is the Triac.